So if a system absorbs heat, its temperature goes up. And that change in temperature is called delta T. The increase in temperature is directly proportional to the amount of heat absorbed. If it absorbs more heat, the temperature change is larger. If it absorbs less, the temperature change is less. It's proportional, there's a proportionality constant, and that is called heat capacity. It's given the symbol capital C. The units of that are joules per degree Celsius or joules per Kelvin. So the more energy that goes in, the bigger the change in the temperature. So we can say that Q, the heat that's absorbed, is equal to the heat capacity, a proportionality constant, times the change in temperature. Another way to look at heat capacity is it's the heat required to change the temperature of a system by 1 degree Celsius. So if you put 1 in here for the change in temperature, then Q is equal to the heat capacity. So if you have a large heat capacity and you put some heat in, you're not going to get as big of a temperature change. The heat capacity depends on the amount of matter, and that's usually measured by mass. So heat capacity is something that depends on how much stuff you have. That makes it an extensive property. Makes it a not so useful property also, because it's going to be different for all kinds of different things. So we use what's called a specific heat capacity. That is often symbolized by C sub S for specific heat capacity, and that's the intrinsic capacity of a substance to absorb heat. That is an intensive property and does not change with the amount of substance. So the heat capacity depends on how much you have. It also depends on what that stuff is. Some things heat up easier than other things. We define the specific heat capacity as the amount of heat needed to raise the temperature of 1 gram of the substance by 1 degree Celsius. Does that sound a little bit like the definition of the calorie? It is. So then we have units of joules per gram degree Celsius. We sometimes talk about a molar heat capacity. That's the heat needed to raise the temperature of 1 mole of a substance by 1 degree Celsius. So that would have units of joules per mole degree Celsius. Those are intensive properties. They do not depend on the amount of stuff. So all of that has been a build-up to this equation. Q equals MC delta T. Some students like to call this MCAT. Q equals MCAT. Because MC delta T. The delta kind of looks like an A, right? So MCAT, however you want to remember it. The heat here, Q in joules, is equal to the mass of the object times its specific heat capacity times the change in temperature. And the units all work out here. So joules equals grams times joules over grams and degrees Celsius times degrees Celsius. So the grams cancel out and the degrees Celsius cancel out, and joules equals joules. The units all work out. Here's a table showing some specific heat capacities of substances. Lead, gold, silver, copper, iron, aluminum. These are all metals, and their heat capacities are fairly low. Aluminum is higher than things like lead and gold, but it's still fairly low. Here's ethanol, and here's water. Water has a specific heat capacity of 4.18 joules per gram degree Celsius. So water has a high specific heat capacity. And this has big implications for climate and weather. Water can absorb a lot of heat without changing its temperature as much as other substances. And so anywhere that you have a large body of water, it's going to moderate the temperature change. What makes a day get hot? Where does the heat come from? Where does the thermal energy come from? It comes from the sun. So the sun comes up and it's beating down and things are warming up, right? The water, this is a picture, I think that's the Golden Gate Bridge. Yeah. So the San Francisco Bay, big body of water, right? As the sun beats down and warms the air, there's a temperature difference between the air and the water begins to absorb heat, absorb energy. And its temperature rises, but only a little bit. If you have something like dirt, dry dirt has a much lower heat capacity. In fact, look over here. We have sand and granite, 0.79, 0.84. So water has a heat capacity 4 times higher. So the water will change its temperature 4 times less than the other substances. So the sun beats down, warms up the air, the water absorbs it, and keeps it from getting as hot. At night, the sun goes down, that source of thermal energy goes away, the air gets cold, and now the water releases energy into the air. We use water as a coolant. The radiator fluid in your car is mostly water because it can absorb a lot of heat without changing its temperature too much. And so we can move heat from mechanical parts out to the front of the car and let it radiate into the surroundings. Any questions about that? This is one of the reasons that we have such large temperature changes over the course of a day. In the summer here, it might be 105 in the late afternoon, and it might get down to 65 at night. 40-degree temperature change. Many other places like Minnesota and Iowa, where I grew up, where it's humid, in the summer their temperature changes more like 10 degrees. You just don't get those changes, and that's because of all the moisture present in the air. Coastal areas see much less fluctuation in temperature because of those large bodies of water. I think that's neat. Okay, this one has a lot of words. Specific heat capacity is an intrinsic property, and so it can actually be used to identify a substance. Do you remember that example we did with the ring that the woman gave the guy, and it was supposed to be platinum, but it wasn't? And they figured it out by looking at the density, right? You can also identify things by their specific heat capacity. Density is a little easier to do practically, but you can do it this way as well. So to determine whether a shiny gold-colored rock is actually gold, a chemistry student decides to measure its heat capacity. She weighs the rock, finds it has a mass of 4.7 grams, and then she finds that upon absorption of 57.2 joules of heat, the temperature of the rock rises from 25 degrees Celsius to 47 degrees Celsius. Find the specific heat capacity of the substance composing the rock and determine whether the value is consistent with the rock being pure gold. These problems need an equation. So we've got Q equals MC delta T is our go-to equation. There's numbers in there. Let's pull those out and identify them. 4.7 grams. What's that? The mass of the rock. So that's M. And then we've got 57.2 joules of heat. That's Q. What do you suppose the system is here? The rock. We're focused on the rock, so the rock is the system, the surroundings is everything else. For the rock, is this a positive or negative? It's positive. It absorbed heat. Money coming into me is positive. And then we've got temperatures. So remember that delta means final minus initial. So delta T means the final temperature minus the initial temperature. Well, what's the final temperature here? 47 degrees Celsius. And the initial temperature is 25. Yes? That is an uppercase C. It's just vertically challenged. I'll make it bigger. Technically, it's C sub S. Different books, different people use it a little differently. Some people even call it S. So I'm going to try to be consistent with the book, but I might mess up. Okay, so 47 minus 25, I believe that's 22 degrees Celsius. You can have a negative temperature change. Negative temperature change means that the temperature went down. Positive means the temperature went up. So here we've got delta T, we've got Q, we've got M. They're asking us for the specific heat capacity. That's this C sub S. So we rearrange the equation. C sub S equals Q divided by M times delta T. I just divided both sides by M and delta T. So Q is 57.2 joules, divided by the mass, 4.7 grams, and the temperature change, 22 degrees Celsius. So we have 57.2 divided by 4.7 divided by 22. 0.5532. This should have two significant figures because the mass and the temperature change have two sig figs. So it's going to be 0.55. What are the units? Joules per gram degree Celsius. Nothing cancels out there. So this is the specific heat capacity of the little rock. Yes?
Are there instances where, in order to identify something, using the heat capacity would be more useful than just like finding the density of the object?
There are times, yes. Some substances you might not be able to conveniently measure a density, but you could do a heat capacity. So is this gold? I don't know. How do we find out? Look it up. So over here, specific heat capacity of gold, 0.128. This is not gold. And if we look at the other things on here, it doesn't appear to be any of those either. It could be a mixture of things. It could be a compound. It could just be an element that's not on the list. So, not gold. Any questions? I feel like I said all of this already.
Yeah.
I did.
Equilibrium.
Yeah, thermal equilibrium. So you get two things, different temperatures. Heat flows from the high thing, the warm thing to the cold thing until they get to the same temperature. So here we have a beaker of water, and we're putting a block of metal into it. The block of metal was hot. It was 55 degrees Celsius, and we put it in the water. The water's 25 degrees Celsius. Thermal energy, heat will flow from the hot thing to the cold thing until they get to the same temperature. What that final temperature is depends on a few things. It depends on the mass of the water. If you have a small beaker of water, the temperature change will be larger than if you had a bathtub full of water. it's also going to depend on the mass and the specific heat capacity of the metal. If this is a big chunk of metal, it's going to release more heat. If it's something with a high specific heat capacity, it's going to release more heat. So in a situation like this, we say that the Q for the metal is equal to negative Q for the water. And it just means that there's an amount of thermal energy being transferred, and it's going from one to the other. Because this was hot and the water was initially cooler, it's going from the water to the metal. But in terms of this equation, we don't need to know which one's hotter or colder. We just need to know that they are equal but opposite in sign. So Q for the metal is mc delta T. The mass times the specific heat capacity times the change in temperature. And that is equal to negative mass of the water times the specific heat capacity of the water times the change in temperature of the water. Any questions? It's like me giving Tommy lunch money. Okay, let's try it. A block of copper of unknown mass has an initial temperature of 65.4 degrees Celsius. The copper is immersed in a beaker containing 95.7 grams of water at 22.7 degrees Celsius. When the two substances reach thermal equilibrium, the final temperature is 24.2 degrees Celsius. What is the mass of the copper block? And why didn't the idiot just put it on a balance and weigh it? But they didn't. Maybe they didn't have a balance. I don't know. They knew the mass of the water, though. It's a little suspicious. Okay, sometimes it helps to draw a picture. Okay, so here we've got the water. And we've got information about the water, and then we've also got this piece of copper. Let's do something copper colored. So we got this chunk of copper, and we've got information about that. So we've got multiple masses and temperatures and stuff, and we've got to keep them straight somehow. Well, what do we know about the copper? We know its initial temperature, right? So the initial temperature for the copper was 65.4 degrees Celsius. What's the final temperature of the copper? 24.2. They give us anything else in there about the copper? They didn't give us a specific heat capacity. We're going to need that, but it's not right here in the problem. We'll have to go look it up. So let's write down what we know about the water. Well, we've got 95.7 grams. What's that? That's the mass of the water. Okay. What's the initial temperature of the water? 22.7 degrees Celsius. And what's the final temperature of the water? 24.2. It's the same. They both go to the same temperature. So I think we've used up all the numbers in there, right? So what we can say is that Q for the copper equals negative Q for the water. Or we could reverse that. It doesn't matter. It's just they're opposite. Well, Q for the water, what does Q equal? MC delta T. So that's the mass times the specific heat capacity times the change in temperature. And I'm just going to put negative in the front. And for the copper, it's the same. The mass times the specific heat capacity times the change in temperature. So there's our equation. What are we trying to find? The mass of the copper. So this is what we want to find. So we rearrange the equation. So I'm going to divide both sides by what I want to get rid of, C, S, and delta T. Now, I've got colors to use. If you don't have colors, then you have to use subscripts. So you've got, subscript Cu and subscript H2O or something like that. So these cancel out. And that's a mess, and I don't have a lot of room, so I'm going to cheat. The mass equals this. What are we missing? We're missing the specific heat capacity of both substances. So let's go look those up. Copper, 0.385. The units here are important, joules per gram degree Celsius, and water is 4.18. 0.385. And for the water, it's 4.18. I don't know why they round that off. It's lame. It's 4.184 joules per gram degree Celsius. Because that's exact. Why drop the 4? I don't know. It's probably best to calculate the delta T separately instead of sticking it in there as this minus that. So from these two numbers, I get the change in temperature. It's the final minus the initial. 24.2 minus 22.7. That's 1.5 degrees Celsius. And for the copper, delta T is the final minus the initial. The final is 24.2, and we subtract the initial, 65.4, and we get a negative number, negative 41.2 degrees Celsius. You can't ignore the negative. It's negative because the temperature of the copper went down. It was a negative change. Now we have all these numbers. Let's plug them in. So the mass of the copper equals, we've got negative times the mass of the water, 95.7 grams, times the specific heat capacity of water, 4.184 joules per gram degree Celsius, times the change in temperature for the water, 1.5 degrees Celsius. And all of that is divided by the specific heat capacity of the copper, 0.385 joules per gram degree Celsius, times its temperature change, negative 41.2 degrees Celsius. Okay. So I've got negative 95.7 times 4.184 times 1.5 divided by 0.385 divided by negative 41.2. And I come up with 37.86. The joules per gram degree Celsius are present in both places, so I could treat them as a unit, and then Celsius cancels out. My unit here is grams. How many sig figs should that have? 2. When I took this difference, I ended up with a delta T with only 2 sig figs. So we're going to say this is 38 grams. If you get negative 38, you should be bothered. You can't have negative mass. We have a negative sign in the front here, and we have a negative temperature change. In any situation like this, you're going to have a positive temperature change and a negative temperature change. One's going up, one's coming down. Any questions? Well, let's talk about work. We're going to do very little with work in chemistry, but this is one type of work we have to talk about. It's called pressure volume work. It's caused by a volume change against an external pressure. So when you have gases expanding in a piston, they're expanding against an external pressure, and so they are doing work on the surroundings. When the gas expands, its change in volume is positive. Its final volume is greater than its initial volume, so that's a positive change. But the system is doing work on the surroundings, so by definition, that's negative. So work equals negative pressure times the change in volume. And here's a useful little conversion factor. 101.3 joules is equal to 1 liter times an atmosphere. Because work is a transfer of energy, right? Pressure in units of atmospheres, volume in units of liters, 1 atmosphere a liter, that is equivalent to 101.3 joules. You don't need to memorize that specific number, no. But at least have it in your head that it exists so you can go look for it. A cylinder equipped with a piston expands against an external pressure of 1.58 atmospheres. If the initial volume is 0.485 liters and the final volume is 1.245 liters, how much work in joules is done? Well, we have our equation. Work equals negative pressure times change in volume. We are asked how much work is being done, so we need to find the pressure and the change in volume. Delta V is the final minus the initial. So final volume, 1.245 liters. Initial volume, 0.485 liters. So that is 1.245 minus 0.485. 0.76. Be careful with your sig figs there, because each of these had 3 decimal places, so I really need to put a 0 out here. That's the change in volume. They give us the pressure. The external pressure was 1.58 atmospheres. So the work is negative 1.58 atmospheres times the change in pressure negative 1.58 times 0.76, so negative 1.2008. What's the unit on that? Atmosphere liters. Nothing cancels out. I can't just do wishful unit conversions and slap a joule on that. I need to use the conversion factor. 101.3 joules is equal to 1 atmosphere liter.
That's 1 liter, right?
1 atmosphere times liter. Well, it would be 1 atmosphere times 1 liter, because the numbers multiply. Yeah, it's weird, I know. So let's just do that down here. So negative 1.2008. How many sig figs did that have, by the way? 101.3. And we're going to convert that 101.3 joules per 1 atmosphere dot liter. So we take that number, we multiply by 101.3, and we get minus 121.64 joules. So minus 122 joules. Yes?
Should the volume be an absolute value? Because what if the volume decreases?
Then it's negative.
So the work is positive?
So if the volume got smaller, the change in volume will be negative. What that indicates is that the surroundings are doing work on the system. Yeah, it's a good question. So the negative sign on this answer is telling me that the system is doing work on the surroundings. Depending on how a question is phrased, you may or may not put the sign in there. If I was asked, how many dollars did you give Tommy for lunch? Would I say -2? No, because the words tell me the direction. I gave him $2. The net change in my pocket account is -2, but it was $2 that was changed. The words are giving the difference, giving the direction. So here where it says how much work in joules is done, it's probably looking for just 122 joules. When you do the math, it comes up -122 because this is the amount of work for the system. The negative tells us that the system did work on the surroundings. And that's one of those things like the oxidation and reduction. You kind of just have to be able to talk yourself through it every single stupid time. Any questions?